Hi again. Let's continue our discussion to understand operations on binary search tree. The agenda of this video is to understand of how we could do traversals on a binary search tree. We understand that there are three types of traversals. One is the on-order traversal, the other one is the pre-order traversal, and the post-order traversal. Yeah, the agenda of this video is just to understand the first one. Yeah, we will go in detail to understand the in-order traversal of a given tree and what would be the most easiest way to write the code for it. Yeah, so what you see here is a binary search tree with three nodes, 22, 11, and 55. So I'm being told what is the address of the root, and I am expected to traverse it using in-order traversal, right? So I understand that the in-order traversal definition would be to traverse the left subtree in an in-order fashion, visit the root, and then visit the right subtree in an in-order fashion, right? So we understand this is the definition. So if you could see, the very definition of it is recursive, right? So it's always easier to write a recursive solution. But if I were to do it iteratively, let's understand of how tough it might have turned out to be, right? So when I'm in the node or when I'm being told that root value is 22, I cannot print that value 22, correct? So what I'll have to do is, jump to its left and see what is the value there. I cannot print it again, right? Because there might be a left child of 11. So I will have to again jump to the left of this node 11 and find out, that there was a null value, and only then realize that I shouldn't print it. And then I come back to this node, to print it on the output screen that 11 is the first value to be printed, correct? So if you could see that these addresses, address of 22, address of 11, and as you move down, you will have to remember it, right? So you will have to have a data structure like a stack to store those values, because you're moving down, you also want to come back, correct? Because you want to come back from 11 to 22 to print 22, and from 22 again jump to 55, correct? Because it's left, root, right? So if I'm expected to write an iterative solution, it kind of becomes obvious that I will have an explicit stack data structure where I store or keep pushing the addresses as I move down, or I trickle down to the left. Right, so we are not looking at an recursive solution in this video. We are just looking at of how we could encache the recursive definition of the in-order traversal and use it to come up with the code for it. Right, so let's go with the definition. So left subtree is to be traversed in order, then the root is to be visited, then the right subtree is to be visited in order fashion again, right? So let's put the code. So let's assume I'm writing an in-order traversal where it has nothing. Okay, let me make place for it. So let me make place for it. Yeah. Okay. Yeah. So let's write a recursive routine called in order, where I am told where to start. Okay, so let's assume I am being told the address of the root. So it is struct node star root. Yeah, or I could call it root, I could call it node X, it doesn't matter. Yeah, it's just the when main calls it, or when the calling function makes a call to in order, it has to tell me the address of the root of the entire binary search. Yeah, that's the point. And I have nothing being returned. Okay, so let's see. Now I understand if the binary search tree is null, correct? I need not print anything. So that would be the base case where I say if root is null, there is nothing to be printed. I just have to go back to the calling function. So I say return. Yeah, but let's say it's not that case. Let's say it's a valid address, which means a tree exists. So I say else, I'll put the else clause where I go by the definition, right? So the base case is if the root is null, I have nothing to print, I just return. Else, I'll do the recursive call, right? So the first recursive call would be on its left, the smaller subtree. And how do you go to the left? You say root arrow left, right? And after you do the in-order traversal of the entire left subtree, I understand I have to come back to the root to print the actual data in it, right? So that would be printf %d, the data in the root, correct? And what would be the next statement? The next statement would be another recursive call, but now not to the left, but to the right, right? So I say in order, that's the second recursive call where the call is made to the right subtree. Yeah. So this is completely based on the definition of in order. And how do we know that it works? We know that it works because we understand every recursive call has a data structure of stack working behind the scenes. So I don't have an explicit stack here, but the compiler does have a stack to remember the calls that are being made, right? So so the first call would start from 22, it will jump to 11, the recursive call here. But when it jumps to the left again, it sees a null, right? And that's when it comes back to the root and it prints 11. So on the output screen, we expect 11 to be printed. After which it will go back to its parent. Okay, there's a right here, null coming back, and then it will go to the parent. 22 is printed, and likewise it continues. So I think our discussion would be complete if we quickly look at the visualization, as in this code. So what you see here on the left, if I could expand it, I hope it's clear now. So this is the code which does the job of constructing a tree, just the tree that you saw. Yeah. So it inserts 22 first, then 55 and 11. So to get you a tree which is just like this, and then it does the job of searching. I've included the tracing of searching here because we didn't do that in a previous video. So we will also see the recursive calls of how things are made to insert, search, and we will finally see of how the in-order traversal of the root would happen. Okay, so initially, if you could see, there is the first call to the main, and yeah, so one second. Yeah, so so the visualization should be clear with this font size. Yeah. So let's see, I have the initial root becoming null. So I'm now trying to insert 22. So let's see of how on the heap you will have a node created. There's a call to get node. So here you see the first node created and its data field being initialized to 22, left and right being initialized to null, and you go back, right? So in insert, there is a node created and its value is 22. Yeah, so the line number 72 that you see here is executed. Let's go to 73 where you're now trying to insert 55. So let's see of how 55 would get inserted to the right. So this is the recursive insertion call. So the base condition is not true, so it has to now jump to the recursive call. So there is one more insert call being pushed onto the stack. So if you could see, there is insert, there's an insertion here, so it continues, and we understand the item to be inserted, it's still 55, correct? So it continues and it understands that a new node 55 is to be generated, and the next job is to link the right of this 22 to 55. So let's see of how it works. Yeah, so when I come back, if you could see, I have 22 ka right becoming 55. Yeah, so let's quickly run through of how 11 could get inserted to the left of 22. Yeah, so the third node on the heap, and that's the link. Yeah, so the link here, the one which is becoming red. Yeah, the left link of 22 is now pointing to 11, the node whose data field is 11, right? So let's go ahead. To understand of how search would do. If you could see, I'm trying to search the node 55. So it will start from 55, it will start from 22, jump to the right, and, see that there is 55. So it's the same search recursive code that we wrote in our last video, where there are two base conditions and then there's a recursive call. So the first 22 is not the key. So I understand that I have to jump to the right. And when I jump to the right, this is the first call to search. This is the second call to search. The key continues to be 55. So let's continue. And it jumps to the right and it says, yes, successful search, right? So we should have successful search being printed here. Yeah, look at the output. So we have it printed. Let's go ahead, the agenda next objective would be to understand of how in order works, right? So there's a slight change to the in order routine that we just wrote. So the change is that, I wrote an if and else clause here, which could be combined as these are the three things to be done if root is not null. Correct. So if root is not null, the three statements here are to be executed. But if root is null, I understand nothing is to be done. So that's the other way of writing in order traversal. So look at this. I say void in order struct node star root. And if root is not null, I understand the recursive calls has to be made. And if root is null, that's obvious. I terminate the call to in order doing nothing, right? So let's see. And now calling in order with the root. Yeah, which is 22. So let's continue. I should see that it should call in order to the left. Now there's one more, push to the stack, the internal stack, the application stack, the call to in order. Now the root value should be 11. Yeah, so it's now jumped to the left. So it says, okay, let's jump to the left, and now it's moving actually to the left of 11, so it should become null. Yeah, it becomes null. Let's continue. 11 is to be printed, so let's see 11 being printed here. Okay, it's got merged with the previous output, so 11 is printed. So it continues, it goes to the right of 11, which is again null eventually. It comes back to 11. Now, if you could see, there are a series of pops happening from the application stack, right? So it comes back to this 22. Now 22 should get printed. Just the way we said it would work. It come here, will become null, and then null to the right, it's going back to 12. So 22. So after printing 22, it will jump to the node 55, go to its left, print with 55, and then go to the right. Yeah. So I think we should be able to see all those things now. So if you could see jumping to 55, it jumped to the left of 55, which is null, and it's now it printed 55 to the right, and then it goes back. So if you could see all the values 20, 11, 22, and 55 would be printed. And yeah, that's the end of of how in order traversal would be done. So continuing, if I'm looking at changing this, let's say I don't want this in order traversal to be done on the code. Let's say I'm looking at a pre-order traversal, it would be a very similar thing. Yeah, it's just that the name changed. I will have to change it from in order to pre-order, right? So if I'm doing pre-order traversal, let's go by the definition, right? So we know pre-order is root left, right? So let's put that. So if root not equal to null, yeah, so it's the definition. So let's put the definition. So pre-order, I should visit the root. So it's printf the value in the root. Yeah, and then recursive calls. So it's pre-order to the root's left, and pre-order to the roots right. Yeah, because we know pre-order is root left right. Yeah, similarly, I'm sure you could come up with the post-order traversal also, where you will interchange the statements in the if condition, and you will follow the definition of post-order, which is left, right, and the printing of the data in the root field, root node. Yeah. Um, yeah, so that was the summary of how we could come up with recursive solutions for the in-order, pre-order and post-order traversal, but we went in depth to understand of how the execution could happen for the recursive in-order traversal. We saw the stack flow, of how things are pushed, popped, and the recursion handles it all. And for us as a developer, the code actually looks really, really simple and easy to understand and remember as well. Yes, so that gets us to the end of this topic of how we could implement traversals on a given binary search tree. Thank you.